So basically what I'm trying to do is, yes, last time we discussed the memory, that was JVM memory, right? But you can have, your data set access the memory outside the JVM. We call it off-heap memory, which is the operating system memory. Now to do that, just go through this article. I think either you need to be my friend or something. I don't know why you're not able to see this, but to do that, you have to enable these settings. Spark.memory.off if enabled, and it must be true. And I will, in through Spark shell, this is how you enabled. I'll show you that command. And also the what should be the off heap size, how much off heap memory you want to consume, so that you should give in bytes. And you can see the details of this in this Spark documentation. The way you enable these settings in Spark shell, it's the same way you enable using Spark submit also. Or you can invoke in your, or you can set this configuration in your code as well when creating the Spark session. When you say Spark session builder.create.conf, you can use and set these properties. So so I'm using Spark shell. Memory heap size is this, and memory of heap enabled is equal to 2. So this must be done. The sample data which we have been using, I'm using the same one. And you also how I'm reading, how everyone is reading the CSV file with header true and delimiter as semicolon and something. Now to persist it, I'm importing this or Apache Spark storage underscore whatever and data.persist. Now here important thing is I'm using storage as off heap. Now once I use storage as off heap, and of course and then I show the data and do some action or something. Now how do I know whether it is storing off heap? You can open the SparkUI. So once you open the SparkUI, you go to the storage tab. Let me see if you can open this in new tab. And if you see in the UI, you go to storage tab, and whatever you have saved off heap, it will show you storage level is off heap. So you can be sure that it's not using the JVM memory, it's using memory which is outside the JVM heap.
There is also one option, like it says replication 1 only, means can we increase that part also?
Replication 1 is because I'm using the, where is that replication 1 you saw? I'm using
storage level. Yeah.
I'm using one except because I'm using local Spark shell. But when you run on the cluster, you can, your replication will be 3x replicated. But you can, this is any RDD which you save, because it's local on my local laptop. So that's why it's saying 1x replicated. But if you're in a cluster, it will replicate whatever your replication factor is. Okay. Now what I do is, how do you unpersist this data? I use data.unpersist. Here I say data.persist with this storage level. Then I say data.unpersist. Then it goes off in the storage level. Now I want to save this data only in the disk. So then what I do is, I say data.persist and disk only, and then data.show. And again, you go to the storage tab, and let me open this in new tab, and you will see it's disk serialized. Right? So because that's the storage level I have given. So that was assignment number 3 or something. So you can do that. Now just follow this and do that. That is simple. Any question? If not, then I want to come back to today's sessions. Let me see, how do I start it from? I will start it from here. Windows functions. I think someone mentioned in the WhatsApp group that these Windows functions are the interview question that person got asked during the interview. So we'll start with the interview in window questions. And okay, I don't want to share. I want to present it. So window functions operate on group of rows and return single value. They are used for moving average, cumulative sum, or accessing the values of the row appearing before current row or after current row also. This is a syntax of window functions. There's a Spark documentation. I think I mentioned the link. This is copied from there. So window functions over some partition distribute by partition column, and the column value, whatever order by expression, ascending, descending, first, last, and we'll see the example. So don't worry if you don't understand all of this. Now, this is a window function, and these, in this window function, one of these things can appear. The window function are split into broadly 3 categories. And by the way, these are all SQL functions. These are nothing related to Spark as such. So if you know SQL pretty well, you would know about these functions yourself. And if you want to understand details of these functions, you don't have to read the Spark documentation. You can go and read any SQL documentation. And most of the SQL, most of the RDBMS like SQL Server or Oracle, or MySQL, they support this. And Spark also supports this. The first is ranking function, and we'll see some example of a few ranking functions. So you can say rank, dense rank, and of course percent rank, entile, row number. We'll not be seeing example of all of this, but a couple of these we'll see example. An analytics function, you want to do cumulative distribution, lag, lead. We'll see example of these three also. An aggregate function, you all know, min, max, count, sum, average, etc., etc. So now there's a window frame. So if you see somewhere there's a window frame mentioned here, you see this window frame at the end. Basically, idea is whatever function you want to evaluate, this is over which data. Now that data is described by window frame. Window frame, which row to start the window and where to end. Like basically, you have millions of rows, and you want to say, I am taking from row number, like row number 1000 to last row or something. So some frame you want to give. So syntax of this is range row, frame start, between, frame start and end. And we'll see example of this. I think if you're not understanding this syntax, that's okay. You will understand with the example, and you can go in and read yourself also later. So what is the frame start and frame end syntax? So you have unbounded preceding, offset preceding. So I will explain it next slide. Unbounded preceding is basically from whatever row you are in, from there till the beginning. And offset preceding, so till certain offset. Current row, whichever row you are in. Offset following from this offset to the the offset following is for the row till this offset, and unbounded following is the last row, right? Offset specify the offset from the position of current row. So if you say whatever offset your current row in, after that you want to go some rows after, then use of offset following, some rows before, you see offset preceding. If you emit the frame end, if you don't emit this, if you emit the frame end, then it omits, then it defaults the current row only. So generally you specify frame end. So we'll see some examples now. So these are some examples. So what I have done is, I wanted to read some data over which you can use this windowing function. So I created MySQL table. So in MySQL, I created this table, and with the name, department, and salary and age, and these are copied from Spark documentation only. If you go to Spark website, this is the example. I added a couple of more over this, and in this I added these values. The name and the department and the salary and the age. Correct. So these are the rows I added. Now because I created this in MySQL, I'm using Spark shell. So I'm using Spark shell. I have to tell Spark to understand MySQL connector. So I use this MySQL connector Java jar. If you are using Spark submit, generally for your production program, you use Spark submit, either through a command line or through some scheduler like Airflow or something. So each Spark submit, command will let you specify the jars. What are the external jars you are using? So Spark jars will be already there in the Spark cluster. But if some jar which is not in the Spark cluster and you want to use that, we call it third-party jars. So you can specify those with --- jars option. I think we covered that during when we discuss Spark submit command. So you specify --- jars option and then give the jar file. Here I'm giving my SQL connector. So I'm using Spark shell, but with Spark submit also it is the same syntax. Then what I do is I say read spark.read format JDBC, because now I'm reading from JDBC. Now what is my JDBC URL? This is the URL, because on my localhost only I have a database called test. This is the database name. In that database I have a table called employees, because this is a table I created. So table name is employees, and user is root, and password is this is what my password I have given. And then option driver, the com.jdbc driver. This is com.mysql jdbc driver is what will come from this jar, and then just load it. This normal SQL, normal Spark JDBC loader. There is nothing, no window function here. It's just setting up an environment and reading the data from the MySQL into a data frame. Now what we'll do is we'll say an example. Now we are creating a temp view and we are using a rank function. Now what that rank function does is, now see carefully here, okay, let's go through this, then I'll tell you the difference. So what we are doing is we are selecting the name, department, and rank over partition by department, order by salary. Now what does that mean? So now go back here and you see these are the departments, correct? So now when you say partition by department, order by salary, so this, for this partitioning is happening, this ordering is happening within each department. So sales is one department, engineering is another. So all row, these and this row for sales, for engineering, this and this row for engineering, and then for marketing, these two rows. So there are three buckets which are getting created. One bucket for sales, one bucket for engineering, one bucket for marketing. Within sales, the ordering is happening over salary. Again, within engineering also same thing is happening. Within marketing also same thing is happening, but it is within each bucket. And that bucket is created by department because we have set partition by department. And we are saying, so we did this rank. This rank is over that each of these three buckets. And then I just, print this. So I'm selecting the name, department, and rank, which is, order by, which is a rank over department, order by salary. Now you see the difference. Within sales, there are three ranks, 1, 2, 3. Right, and if you see the record, Lisa, Alex, and Ivan's are sales. So Lisa, Ivan, and wherever the Alex is, these are the sales. So based upon the salary, the rank is given. Lisa's salary is 1,000, then Ivan's salary is 3,200, and Alex salary is it's 10,000, 32,000, and 30,000. Right. So this is how the salary is ordered, because this is what we have told. Same is the case with the engineering. So 1, 2. Now there's a difference. Now you see Chloe and Tom. So if you go to engineering and check for Chloe, and it has, she has 23,000, and Tom also 23,000. Right? Both belong to the same department and both have the same salary. So in this case, both are given the same rank. Now Paul is the last one, right? It has the, where is Paul? It has a maximum salary, I think, this one, right? Now with the rank, you will see with the rank function, you will see it has skipped 3. It has directly jumped to 4. So 1, 2, 2, 4, because there were 2 people with the same salary. Implicitly, it assumed that because it was supposed to give 3 to this, but it has given 2. So it consumed 3 already. So it will not consider 3. It will jump to 4 already. So this is what rank does. Now there is another function called dense rank. Now same thing, everything's same. Only thing I'm doing is I should be using dense rank. I did not copy the, I think I kept this thing rank, but I assume this is dense rank, dense underscore rank. That's the function. This is what it is. Right? Select name, department, dense underscore rank over partition by this. Ignore this, this statement. This is the SQL statement.
You have added it at second part in the same query.
Oh, right. Sorry, my mistake. You are absolutely right. I have added rank and dense rank both because I wanted to see the difference, show the difference. You are absolutely right. So rank is this and dense rank is this, correct? And so see this, rank is over whatever the previous statement was. This is the rank, and dense rank is same thing, but I have used, the dense rank over, partition by order, partition by department, order by salary, and this is what I have given as dense rank from employee, correct? Now in the rank, everything is same. Only difference you will see is in the Fred, Chloe, and Tom, the rank had 1, 2, 2, and 4. Here you will have 1, 2, 2, and 3. So if you want to not skip the rank, not skip any digit because the salary is same or whatever column you are ranking over, if that value is same, then you don't want to skip this, then you use dense rank. Otherwise you just use rank. It all depends upon your business logic, the business problem you are trying to solve. But these are the two functionality which Spark is providing with rank and dense rank.
And in that method, if we don't give this rows between unbounded preceding and current row, what does that brings the difference? Means what difference does that line bring?
So let's try that. I did not try it, so we'll try that right away. Let me see. I will open the Spark shell. Let me open the Spark shell right away. Okay, and first we'll read this data. Oh, I have that this thing. I have to read this JDBS. JDBS I have to use only this. Hopefully, to is the okay. My mistake. I should have done this. Control R. Controller hyperpin jars. And this is what I want to use. Okay, so now what I'm going to do is I'm going to paste what I had. Detected this. Now let me print this. So this is the records you would have. Now, what were you saying? Let's do that. Window function. Get to only this. Now you are saying, sorry. What is this? So it's arena. Oh, because I did not create the select dance for name department and strength partition by. I think I need to create that EMP, right? That I did not create. This one. This one. Now I'll run this. Then show 1 2 3 1 2 2 3, and you are saying now if I don't give this, this is same because there is no difference. When you say unbounded proceeding, it starts from the beginning. When you say current row, right now we are not processing anything, so it's from beginning till end, so it's doing the same thing. But if you are in between the processing and then you issue this statement, then you might get a different result, because that result will be from your current row till the beginning. Now here, because it's from beginning till end, whether you give this or you don't give this, it's coming at the same, it's giving the same result. But if you are somewhere on your current row and then you go beginning from that row till the beginning, then you might see the different result. So that's a difference.
Do we need means there can be some kind of scenarios where we will need this kind of thing, like to read something above this or below this?
Now above this and below this is the different, that's lag and lead. Here you are just creating the rank. Rank, you might need this sometimes. I have not seen scenario where you generally, when you read rank in big data processing, because in big data you are talking about billions of rows, you will not, mostly you will not be needing to use the preceding and current row or something like this. So because maintaining this cursor or the pointers within billions of rows is a problem. So generally in Spark you will not be using this rows between and all of this, but of course you will be using rank and dense rank quite often, because you would want to know, like this is one example. You would want to know what's the maximum salary, second maximum salary, third maximum salary. This is one way of doing this. And depending upon the business logic, you might need to do. So I have used this in some use cases. This I have not used. This I have not used ever. So but you might need to use rank and dense rank.
Okay.
Does this answer your question?
Yeah.
Okay. Now let's move on to the next one. This one was a cumulative distribution. I think we covered the dense rank. So this was a cumulative distribution. So in the cumulative distribution, it's pretty simple actually. So you will see, right? So let's go through this. So the select name, department, age. Now cumulative distribution over partition by department, order by age, range between. So you can skip this for this also, by the way. So you can say partition by department, order by age. So what it will do? And you are using a cumulative distribution function. and you're doing over the department. So how many departments we have, how many, how many rows we have in each department. So 1, 2, 3 for sales. So it will be, and you are saying order by age. So first age will be, it's sort of cumulative distribution of the first row is 33%, correct? Because there are only 3 rows. Second is 66%, and third is 100%. So cumulative, the records distributed over these ages are in this range. That's what it means. Same is the case with engineering. So you have 4 rows, correct? So first row cumulative distribution is 0.5, then 0.5, 0.25, 0.5, 0.75, and 1. It's a distribution. So that if over 4 rows, the distribution will be 25%, 25%, and so on. So that's what it is. For marketing, there are only 2 rows. So 50% and 100%. That's how it is. The next one is, now I try to explain the lag and lead. This is a program which is not a Spark program. This is not a Spark thing. This is normal SQL. I've tried to tell you what is lag and lead and how does it work. Right? So take this example. I have these 3 IDs, 3, 1, 2, and I have these names, and I have these values. Now I run the following lag query. Let's see the result. Select seller name, which is this, sale value, which is this, and the lag, this is third column lag. And what this lag will do is order by sale value, order by this as previous sale value. So now we are ordering by this, and you will see, it, or by default, it's ordering in the ascending order, 77,000, 12,000, or 25,000. So now what is the previous value of the previous sale value? The value of the sale value for the previous row, what that is for this row. There is no previous row, right? Because it's the first row, there is no previous row, it comes as null. What is the previous row for this? The previous row for second row, it's the first row. The previous row for second row is, and what is the sale value of first row, which is the previous row for second row, is 7,000. So 7,000 will come here. What is the previous row for third row? Is the second row. So what the sale value of second row is 12,000. So that will come as previous sale value here. So that's what this function does, lag. This is a normal SQL function. There's no Spark here. So I have tried to do this in Spark and see how it gets done. So lag, order by salary, value of the above row salary, right? That's what we discussed in lag column. Null for first in the, because we are doing the partition of a department, order by salary. Lead, value of the below salary. So it's very similar to this, but now in the lead, value will be the of the row which is after the current row, correct? And we'll see example of this. So I try to calculate both lag and lead in the same SQL. So you say select name and salary. So name and salary will appear as is. Then you're saying lag over partition by department, order by salary. So for within each department, I am calculating this lag. That's what partition by department means. Within each partition, lag and lead will be calculated. How lag and lead will be calculated? Order by salary. Now, if you see, you're calculating the lag for this lag means the previous row. For first row, there is no previous row, it's coming as null. For second row, and it's it's a salary, by the way, because order partition by department and order by salary. For the second row, what is the previous row? This one. And what is the salary here? 10,000. So that's appearing here. Same is the case with third row. Now what's the lead? So I'm saying lead salary 1,0 over partition by department, order by salary as lead from employee. Now lead is again salary. So you will see the next, what is the next row for the first row is the second row. What is the salary of this? Is 30,000. For this second row, the next row is third row. What's the salary of this? 32,000. And here it is appearing 0. So what I'm saying is, for first, just make it 0. This is what it means. So when you don't find the next lead, then just make it 0. This is what it means. So that's why it's appearing as 0. For Fred, same thing for our, because it's partitioned by or department. For each department, it is doing this, right? So that's about lag and lead. Sometimes it comes very handy in your business logic, right? If you do, honestly, I did not know these functions 3-4 years before, and I did a lot of workaround to get these values. And when we came to know about these functions, it became pretty easy. So knowing this comes very handy when you are stuck with some problems which need this. So one is Untitled, which I am not doing. I think you can do that yourself. Um, Unbounding proceeding, when you mention unbounded proceeding, it's the first one in the partition. When you say unbounded following, then it's the last one in the partition. So that's what it means. And you can see these are some references. This is pretty good. This guy, Jacek Kowaski, is very good. He's given a lot of YouTube video talks. You should see his YouTube video, and he's written a Git book on on the Spark as well as the Spark streaming as well. So you should go and look into this. It's pretty good. So he explained the concepts with examples and then explained it very nicely. And so you should go and look at these URLs also. I think that's about it. Any questions, any comment you have?
What will Untitled do actually?
I forgot that. I think we can read that in the Spark documentation. Untitled. It's normal SQL function. You can search for any SQL Untitled. And this is what it is. You'll see this documentation everywhere. So whatever it's in all places, distributes row in ordered fashion into specified number of groups. The groups are numbered starting at once for it. So you go through it. This is normal SQL. I think this you can see better example in week for weeks. This explain week for week explain better. So it's just distributing of some row into certain groups based upon certain conditions, hopefully. So the window function to distribute rows of an ordered partition into predefined number of equal groups. This is grouping, just sort of creating bucket. Right? Just go through this. It's some sort of bucket is creating using these groups. I never use the central function, but it will be good if you go through this yourself. Any other question? Okay, now we'll cover the Spark UI. So what we'll do for Spark UI is I will write some query on the Spark SQL, and then we'll see the Spark UI, which is the values in the Spark UI, which is resulting as part of that query. So let me run this query in the Spark SQL. And by the way, when you start the Spark SQL, you can see your URL, or even Spark submit also. You can see the URL is this. So I'll open this URL after running these queries. Sorry, why did I copy that? I copy this. Okay, good. I copy this. Okay. Good. It's just something I'm running. Just getting some converting this sequence into the DF, and then department, and then I might be doing a join somewhere later. Did I not copy that? Yes. Let me copy all three now. Okay. This is first. And now, is that all? Yes. And by the way, you can see the Spark UI, on this. It's pretty well explained on this link. So you can go and look at this. What I'm going to do now is going to the Spark UI here. Copy this. And paste this. So this is what I see, right? Now you see jobs, you see stages, storage, and we'll go through it one by one. We'll just follow the. How can I open this in another thing? Let me open Firefox. Put it there. Correct. So now we'll go through this one by one. We'll close all of this. Okay. Now on the Spark UI. So let me start from here. You will see Spark jobs, stages, storage, execution, storage environment, executor, streaming, and all those things, right? So it starts appearing here. So we'll go through each of these one by one. And I might not follow all these slides, but what this jobs is. Jobs show you any action you have performed. So every action will come here. And because I have to perform show, so I, because this is what I've been doing on my Spark console, and this is what is appearing here. So this is what is appearing here. I can click on this. Once I click on this, it goes to details of this. You can see the event timeline, right? The executed driver added and everything, and you can see the DAG visualization. This is, basically how many stages and all that you have, and then some exchange might happen. And oh, this is the window operation which I ran. Sorry, this is for the previous window operations I ran. So that did some exchange or something. So you can see that, you can see the details of this. Generally, because Spark SQL, it doesn't show your code, but if you have written your own code, your code, and you're seeing this UI which is generating from the action of your code, then you will see your code lines appearing here. Your name of your class file will start appearing here with the line number and everything. So you can see that from this. You go to jobs, click on the job, and this will start showing the details of that job. And generally, for your code, you will start seeing, because in your code you will be reading some file, you will be doing some operations, and you will be having more than one executor. Here it is showing only driver, but it will showing executor 1 added, executor 2 added, executor 3 added. It will show all of that in this graph. This graph is not that of important generally. This is what generally you look at for this job, what shuffle happened and why it happened, and what's the code. Sometimes what it has come very handy for me when I see shuffle has happened and I realized I am doing some count which I was not needing to do, and that was triggering in some performance issue or something. So it comes handy that way. So you can see that. Then stages, of course, this is what I showed you. It's the same thing you can see here also. Thus in the stages, how many stages you have, you can see the DAG visualization here for this. Some shuffle already I created while showing it, console. Something happened, window operation got run, and some map partition happened here. And I don't want to see additional metrics. You can see generally I don't read much, but this is what becomes very helpful when you're running your code in production. What you want to know is how much data is getting shuffled, because more data shuffle means it's a more problem. So you want to see that how many shuffling is happening here. The tasks, you can see the task for the executor. So this is the additional metrics of executor. Executor is nothing but my driver role is executor, because I have a Spark shell on my laptop. So it started 100 tasks for the window function which I generated. It completed all 100 tasks. And of course, it had some this shuffle rewrite size. And you can see each of these tasks. In my case, it's showing driver, but if you have more executor, it will show the executor ID here. And yeah, so this is about the tasks. You will see these thing task wise also, these things value getting populated. And if you see error, and I think you can click on that error and see what the error is for each task. So that's about the jobs and stages. Let me see what else is in stages. Yeah, for each action, whatever the stages are there, it will show all of that. Then you see storage. This I think I showed you. Once you do caching or persistence, it will start appearing the storage, the LinkedIn profile which I showed you. You can follow that and see the values appearing here. Environment, whatever environment you're using, sometimes it comes handy. Few of the things which I want to see, I think there is some system properties which are getting applied here. Not this. There is one Hadoop properties which are getting applied. Whatever you have set, your HDFS or something, what you have set, you can check that here. What setting Hadoop is taking. I don't use it much, but once in a while I end up referring to this. System properties is whatever your system property you set using -d option, those start appearing here. And the class path entry, this I refer very frequently, because sometimes I set the class path and on 2 occasions I see problems happening. One occasion is that some jar with different version is in different folders. I try to figure out, and that causes problem during runtime. So then I try to figure out where each jar is coming from. So I tend to look at this class path entries and figure out which 2 jars that particular component has, and which folder they are coming from. So I look into this path and everything. So this becomes very useful in those scenarios. Another scenario is that I included some jar, and the jar, the code is throwing that class not found exception because that jar is not getting detected. So I looked into this and figure out, whether that path where I have stored the jar is appearing here or not. So these are the some system properties. Executors you can look at. So any job you submit, it will have an executors, and right now because I'm using Spark shell, so it will have only one executor, but you will see a lot of list of executors here. And you will see each executor is doing how much shuffle, how much shuffle read, shuffle write, how many tasks it has. And of course, if you want to see the thread dump of each executor, you can go and see the thread dump also. Sometimes it helps if you want to see how many, how the system is behaving under the hood. So you might want to look at the thread dump as well. But yeah, this comes handy when one important thing that you want to look at this is this. Let's say your machine has, I'm talking about cluster, not about your local. Like I'm showing it on my local, but in your cluster, you have, let's say your cluster, to keep it simple, consists of 10 nodes. And you will have 10 executors. Generally, the relation between executor and node is not 1-to-1. One executor, if it is one node, it has good capacity, it can have 2 executor also, or 3 executor also, based, and that you can specify by submitting your Spark application how much memory each executor can have based on that setting. One node can run more than one executor also. But to keep our discussion simple, let's say there is one executor per node. Now, and that executor, but each executor is having, let's say, 32 cores. Generally in production, you will be having 32 cores or 64 cores or something like this. Now, what you should use is, if you see, come here and see the executor, your executor on that particular, one executor is using only, let's say, 10 cores. Basically, your 22 cores are wasted. Like 2 cores you can keep system operation or something. So out of 32 cores, you want your Spark program to use 30 cores at least. If it's not using 30 cores, that means you have not configured your Spark program to run optimally. So this is very important thing you should check, because you over provision your cluster and you don't use the cores. So that means you're paying for that hardware but not using it. It's a waste, and your Spark program could have become faster if you could have used all the cores. So there's a setting in the Spark configuration. I think I'll open the Spark configuration page, and you can specify executor, core per executor or something, and you increase that. So executors should start using on one node. If it is running one executor is running, it should start using as many cores as possible. If more than one executors are running, then let's say 2 executors are running on one node, then both executors together should start using, and you can see that on one node, if 2 executors are running, the address will be same for both executors here. So those together should use almost all the cores except 2-3 cores you want to leave. You should use all the cores of that particular node. Then your task will be much faster. So these are the, and then of course SQL. I think we saw SQL example last time. So when you're reading the file or something, you can see here, right? I want to, generally I tend to see, I think I discussed last time also. If I'm reading a file, you can see the plan also here, by the way. The physical plan only it will show you. And when I'm reading a CSV file, it will show me the details that which file it read and which folder it read from and how many files in that folder it read, right? Folder might have 100 files, but I'm reading it based on certain condition. It might have read only 2 files or 5 files or 10 files. So it shows all of that information to me here, right? So you can click on this. In this case, it doesn't matter because it's all local and everything, but this comes handy, during debugging such information. This is about Spark UI. Any question on the UI part? Okay, so use this UI quite extensively. Use your plan. I think we discussed the planning, earlier. Use your plans quite extensively. If you do your plan, if you look at your plan, you will come to know a lot of problems yourself. And once you have optimized your plan, and then further things, you can look at your UI and see where the problem is and whether your Spark job is using all the resources or not. So that's about the UI. Now what we want to cover next is, so this UI is done. Window functions are also done. Now I want to cover the range partitioner. I think someone asked for range partitioner last time, and we'll cover the range partitioning, how it works under the hood. And what I have done is I have gone through the Spark code, how Spark code, how range partitioning is written in the Spark code. And I have copy pasted that part of the code and try to explain here. So range partitioners, I will go next. Let me share. So while it's loading, so data, if you go to the dataset API, in the dataset you have the repartition by range option. So you could use that option to repartition your dataset. And I looked at the test cases. I am saying share, sorry, mistake. Should say present. Hope it loads fast. Yeah. So data set is repetition by range. So I look at the code. So data frame suite, it's a Spark code. So there they have their testing repartition by range. So we'll see how they are testing. So they have some 0 to 9 and whatever. The here what we wanted to check was they're repartitioning by range. They're passing some size and some value, in some order, and based upon that they are repartitioning. And I'll explain it below. How is that working? So if you go to repartition by range, this is the partitioner.scala. And if you go look at the repartition by range and look at the documentation, let's read out the documentation. It's coming from the source only, right? From the dog's mouth, from the horse mouth actually. So it returns a new data set partitioned by given partitioning expression into number of partitions. So here you are passing number of partitions, and partition expression is the column over which you want to partition basically. The resulting data set is range partition. At least one partition by expression must be specified. When no explicit sort order is specified, ascending nulls first is assumed. And we discussed that ascending null first, ascending and all those things. Note, the rows are not sorted in each partition of the resulting data set. Note that due to performance reason, this method uses sampling to estimate the ranges. Hence, the output may not be consistent. Since sampling can return different values, the sample size can be controlled by Spark. This is the configuration. Config by spark.sql.execution range exchange dot sample size per partitions. So based on this sample size, it will try to sort of find out the ranges of this. And I think I have example of this further. Let me see if I have example. Somewhere I have example. This is the example. So let's come to this later. So this is what the this is what the where were we? Yeah, this was the range repartition by range in the Spark code. Then it's a details. A logical plan is another method in the data structure which provides the same. So repartition by this, they copy pasted this repartition by range, and it tries to repartition. It tries to get the sort order. If nothing is given, it just try to get whatever is the default value, and then in that implementation, it just repartition by expression, sort order, and logical plan. Now this logical plan, the idea to show here is that the repartition by range will internally use a logical plan, and this logical plan would have already calculated it. When you submitted your Spark job, the first thing it does is to calculate the plan, and it would have used that plan and the sampling and the sort order which are given to come up with the to repartition your data set by range. Now this is too much code. Let me skip that. I think you get the idea. We'll see the example. Now there's another class called partitioning.scala. So partitioning.scala has range partitioner for RDD. What we saw above is the data sets of Scala, which used for data set and data frame. That's how it works. But if you're using the RDD, then how range partitioning works, right? So we'll just read this out. This is for RDD only. Represent a partitioning where rows are split across partition based on some total ordering of the expressions specified in the ordering. When data is partitioned in this manner, it guarantees given any two adjacent partition, all row of the second partition must be larger than any row in the first partition. Right? Because when you're specifying range, let's say you're specifying a range of salary. So if the salary is, let's say, 10,000 to 20,000 might be in the first partition, and 20,000 to 30,000 might be the second partition. So that's what it's trying to say here, right? You should use the ordering. This is a strictly stronger guarantee than what order distribution, or forget this, we are not using. So this is the implementation of range partitioning in using in the RDD class. The RDD uses this range partitioning, class. So I will not go into details of this, but I just wanted to show you this heading. So let's see the range. I copied this, from this URL. So range partitioning by range. Let's see the example of this. So these are the lines. These are the records, whatever 1, 2, 3, 4, whatever, right? And what it does is this is a records called orders to partition, and it is repartitioning by range, and it's giving 3 partitions and based on the ID, right? So this, I'm assuming these are the ID columns, correct? And then you see the output. So output would be, of course, this is a test case is checking the size should be 3. You can check the data set dot partition size or something, it will show 3. Now here is what it's doing the partition. So with ID 10, 11, 12, 13, 14, these are coming in one partition, 15, 16, 17, 18 second partition, rest are in third partition. So that's how the repartition by range ended up being. So again, these are the number of partition, and this is the column of which partitioning has to be done. Okay. You can read this again. This is the same URL where from I copy paste the code. RDD range partition has little different implementation. So I'll skip that. I'll skip that. Because RDD range partition, RDD we should not use. Generally, we should avoid. So I'll just stick to the data set range partitioning, and I hope you understand how the data set range partitioning works. Any question? Good. I think it's pretty simple. You see the example shows it's pretty simple how it internally does. You can see that code here, here in the data set. You can go through this implementation of this in the partition.scala. Go through the implementation of this if you want to see how it is being. You know an implementation also. Okay, so these are the 3 topics which I had. Any question on these topics? If not, then I want to show you what will the next week. Next will be your last session, and what we'll cover in the not this 4. I wanted to open 6th. This one. So next we'll focus only on the optimizer. How optimizer works. Internal details of optimizer. I'll just give you a quick walkthrough of that so that you can read if you want, and and then we can go into details in the next session. Even if you don't read, we'll just go into the as much details as we can. Now, question from Amrita is, why do we use off-heap memory for storage? Is there a particular use cases for this? I mean, everything depends upon your everything depends upon your business logic. Generally, the way we might use this, I will give you some scenario. This is one scenario, but combination of other scenarios might be possible in your use case. The scenario is that you have some clusters which are being used where there's a lot of memory, but not all memory can be given to Spark, because there might be some other reporting systems or in reporting tools are running, or something else is running. So, but if they are not running, Spark can use the memory outside. So that could be one use case, because even if those systems are not systems run slow because Spark is consuming most of the memory, it should be, that is fine. So in that case, you say, okay, we are dedicating out of 64 GB memory, we are dedicating only 30 GB memory to Spark. Rest of the 34 GB is outside Spark. So if that's your topology, then use off-heap. That's one scenario. Other scenario is, for whatever reason, you are having huge data sets, and if you store this in the Spark JVM on the executor, on the worker nodes in the executors, then it's going to consume. Then Spark is going to have very limited memory for other things. So, and if you want to avoid that, then maybe you can use off-heap memory outside the Spark. So these are first few of the examples, right? There is no hard and fast rule that whether you should do that or not do that. It all depends upon your business application and the business problem you're trying to solve. So I will quickly give you a very high level layout of how this optimizer works, and we'll go into details of this. There is a very good YouTube video on this. I think I might have a link of that also towards the end or somewhere. If not, then go to YouTube and search for Spark Optimizer. So the way, this is very important. This you should remember always. When you run when you have SQL query or use a data frame, and you submit that to Spark. What Spark does it's first of all creates a unresolved logical plan for you, and we'll discuss what that unresolved logical plan is. Then it refers the catalog, like whatever table names you are given in SQL query, whatever columns name you are referring in data frame, everything. It refers the catalog to validate all those are good. Then it becomes a logical plan. Then it runs some sort of optimizers. Like there are some optimizer, catalyst optimizers, and a couple of optimizers. It runs those and converts the logical plan into optimized logical plan, and we'll see one example of that also. And then from the optimized logical plan, it converts the physical plan. So what is involved in converting the optimized logical plan to physical plan is it just converts into RDD. At the end of the day, everything which executes in the Spark executes in RDD. Even though you are using data frame and SQL query, but this physical plan will be converting into RDD. And then there's a cost model which gets over this, and we'll discuss about this cost model. This is cost-based optimization. So I'll give you a gist of this. What is this optimization and what is this cost-based optimization? I'll give you some hint, and then we'll cover in details next time. Then it applies cost-based model, and it considers a selected physical plan, which, oh, sorry, my mistake. This is a physical plan, which I'll show you the difference between logical plan and physical plan. It is not converted into RDD yet, but it sort of know. For example, in logical plan, you can say sort. In the physical plan, you tell which type of sort you will do, right? It's a merge sort or any other sort. So that's the difference between optimized logical plan and physical plan. Then you come with the cost model. I will tell you the cost model here and the optimization here. What's the difference? After cost model, it comes with the selected physical plan, and then code generation happens into RDD, and that's how it runs. So we'll go into these details. That there's a rule-based optimization, the cost-based optimization. The rule-based optimization is what this is. Cost-based optimization is what this is. And I'll very quickly cover what that is. And this is I think this is the link. This is the video. Most of this material come from this video only. So you should go through that. I will not go into details now. I'll keep it for the next time when we go into details. How this plan gets converted. This is a logical plan. You see aggregate project. So this query the person is running. Select some from t1.id, t2. There's two tables, t1 and t2, table 1 and table 2. He's joining this table and selecting the ID, and then 1 plus 2 plus t1.value as v. Right, t1.id and t1.value, where condition is t1 and t2 IDs are same and t2 ID is greater than 50,000, something like this, right? So this is your non-optimized plan or something. So aggregate project filter and all. And once you go to the next, it becomes your logical plan, because you see there is aggregate project filters, and this is the join. And logical plan describe the computation without data set. So in this case, it's more or less similar, but we'll see the difference here between optimized logical plan and the physical plan. Here you see the aggregate, and here you see the hash aggregate. Here you saw join in the logical plan. In the physical plan, you'll see sort merge join. So that's a difference. Then the one of the optimizer, like we saw this. We are on slide number 14. Let me go back to this diagram. Now, how this optimized logical plan works, like how this optimization happens. So some example of that is here, where you see this example. We are adding literal 1 and 2. Right? Spark will check your DAG. This is DAG, direct acyclic graph. So here you are adding literal 1 and 2, and instead of having this tree structure, it will calculate this and keep the literal 3 for you. So that every time this calculation can be divided, instead of 3 node, it will have 1 node. So this is one, and there are many such things, and we'll go into details of this. Right? One another thing could be that you are doing filter here. First you are doing join, and then you're doing filter. So why can't you do filter here only? So it might reduce a lot of your, you are joining, you are reading this table, and then joining. And then over this table, you are saying, get me the records where ID is greater than 50,000. Well, why don't you get the records? Spark will check and figure out, okay, this condition could be applied here only. So that instead of getting millions of records, possibly you'll get only hundreds of thousands of records. So it will push the filter down here, right? So that's what it will do. That's another optimization it will do. So it'll combine all of this, And another thing it will do is column pruning. If you're selecting only few columns, and this table has hundreds of columns, this table has hundreds of columns, but you need only few columns, so it will do column pruning and select only the columns which you need. That's another thing. So it sort of creates into tree. And then I'll skip all of that, and I'll just tell you the, I think at the end is a good slide to tell you the cost-based optimization. So let's see cost-based optimization, have I added it here or not? I guess, yes. Cost-based optimization, right? This cost-based optimization is basically, it's the same thing. What it's going to do is, when you're joining these two tables, there's a build side table and a port side table. Smaller tables is chosen as build side table to have a hash table. So you have two tables. Table 1 is 500 GB in size. Table 2 is 20 GB in size. So, but there's a filter on 500 GB table, correct? So, so this is 500 GB is 5 million records. When you apply filter, it becomes 1 million record, correct? And only 100 MB. So now, if you don't use cost-based optimization, this table, this is how the join will happen. So you will have the smaller table is build side. In this case, this smaller table it considers as this table, which is a build side table, right? It needs that for optimization. Like you might have heard of map side join, or you might even try to broadcast this table, right? To optimize. So, knowing which table is smaller helps Spark in optimizing many things, right? So one of the things is doing the map side join, using the smaller table as a map side join table, trying to broadcast a smaller table. So if this information Spark gets wrong, then it will cause problem. So what cost-based optimization will do is it will figure out what is the cost for each of these node, and it will figure out after filtering it's coming as 100 MB only. So what it will do is it will consider this as a smaller table, and which will come as a build side table, and it might even do this predicate push down, which means it will do the filtering at the source, and it might consider this 100 MB as a broadcast variable, and put as a broadcast into all the executors. So this is how cost-based optimization is done. We will cover all of this into a lot of details into the next session, but this just wanted to give you a high-level overview of how it works. Any question, any concern? Okay, let me stop the recording. Just give me a second.